All right, continuing on this journey of section 4.5, integration by substitution. So today we're looking at that definite integration. We're going to play around with the calculator a little bit again. And we're also going to discuss even and odd functions. So let's go ahead and talk about a definite integration here first. And I'm guessing that we probably are all pretty good with this at this point in time. But I want to show you some different things that could happen when we do a U substitution and the way they may test you on this. So here we got 3x squared times the quantity of x to the third plus 2 squared dx from 0 to 2. So we're going to let our u, again, be that quantity. That makes sense to me, x to the third plus 2. So when I set up my integration, we have to be very careful because these values are talking about x values. They're not talking about u values. So there's a couple ways around this. One, you could switch these values, since they're x equals 0 and x equals 2, to u's by plugging 0 and 2 in here. So if we gave you 0, f of 0, if you think about f of 0, if we plug in 0, we would get 2 out. So instead of a 0 there, we would have a 2. And if I looked at f of 2, well, that would give me 8, that would give me 10. So I could have the integration from 2 to 10. Doing my u substitution, I know the derivative of 3x squared, x to the third plus 2 is 3x squared. Getting a little ahead of myself there, wasn't I? Dx. So I have that integration there, or that part of my integrin of what I want. So I'm looking at the integration then of just u squared du. The integration of u squared is u to the third over 3 from 2 to 10. I go ahead and plug in my 10, plug in my 2, subtract the two values, and we're done. So we have 10 to the third over 3 minus 2 to the third over 3. Again, if this is extended response, I'm leaving this. I'm not going to mess with it. We could play around with it. We'd have 1,000 there, wouldn't we? Minus 8 over 3, so 992 over 3. Again, not of use to me at this point in time. What if we don't change these? What happens? Well, if I'm not going to change them. I'm just going to go to an indefinite integration at this point, and we'll come back to these values. So, and this kind of gets a little tricky because we go from a definite into an indefinite, and I don't necessarily like the notation of this because we lose that and it makes it look more indefinite. So we're going to integrate u squared, which is u to the third over 3. I'm going to put that bar there because I know in my mind this is a definite integration. But these aren't u values, are they? So if I were to go ahead and plug in those values, I'd have to replace these u's with x to the third plus 2 to the third over 3 from 0 to 2. Now if I plugged in my 2 to the third, we get 8 plus 2 is 10. So I get 10 thirds over 3. Minus plugging in my 0, 0 plus 2 is 2 to the third. So I get 2 to the third over 3. So notice it can be done this way. We just have to get very careful because we have to change those u's back into x's to make it that definite integration. I don't see much of a reason to do this method here, or this way, to think this way, because we don't need to come back to our x's. We've already switched everything over into those u's. The only thing that you might see is that our top number and our bottom number, we normally see our larger number on the top and our smaller number on the bottom. However, doing a u substitution, we could see the larger number on the top and a smaller number on the bottom. The smaller number on the top and a larger number on the bottom. I'll get it straight here in a little bit. All right, so that's the way I would look at that. So I do want to show again just a couple more examples. The reason I bring this up and changing those, sometimes on the exam and on tests that I give here, I may tell you if u equals x to the third plus 2, what integration would this go along with? So it's not necessarily a problem that you would solve completely out. You would just rewrite it in this form here. And that would be the answer that we're looking for. All right, so I do want to play around with a couple more, just changing those x values into u. So here I'm going to have my u equal 1 plus x squared. So my du is going to be 2x dx. Again, I don't have a 2 in there, so I'm going to have a half du equals x dx. My 1/2 is going to go out to the front. Instead of going from 1 to 3, now if I plug in 1, 1 squared is 1 plus 1 gives me 2. If I plug in 3, I get 9 plus 1 gives me 10. Well, that's odd. I'm going from 2 to 10. Doesn't always happen that way. But we go from 2 to 10, don't we, on this one? And then we have u to the 1/2 du. The integration of u to the 1/2, we do, oh, sorry, it's the third root, isn't it? So it's to the 1/3, sorry. So we have then 1/2. U to the 1/3 is u going to integrate to u to the 4/3 over 4/3, which gives us 3/4. And we're going from 2 to 10. We can clean that up just a little bit. We have 3/8. And we're going to multiply that by plugging in our 10. We have 10 to the 4/3 minus 2 to the 4/3. I have no idea what 10 to the 4/3 is or 2 to the 4/3 is. Doesn't matter. That's going to be our answer. That's where our calculator would come in to play if you wanted to plug it into your calculator. Let's see, if we wanted to do that, we would definitely go into our math, and number 9 is our infinite. We go from 1 to 3 of x, there's my x, cube roots. So in that order, I got to do math, number 4 of my 1 plus x squared dx. And we end up with 7.134. Now, if we want, we could go ahead and put this in our calculator and see if we don't end up with the same thing. I'll cross my fingers that we do. So we have 10 to the 4/3 minus 2 to the 4/3. And then we're going to multiply that by 3 and divide it by 8. And look, hey, we did. We got the right answer. Woohoo! 7.134. All right. I'm going to skip this one just for time's sake. It's going to work out very similar to the one we just did. I wanted to do a trig problem here real quick. So we have the sine of 2x. We let u equal 2x, which is always, remember, u is normally going to be the angle that we're working with. Not always, but generally speaking. So we have 1/2 du is going to equal our dx. So we're going to integrate, and we're not going from 0 to pi over 2 anymore. I plug in my 0, excuse me, 0 times 2 gives me 0, and 2 times pi over 2 is going to give me pi of the sine of u du. Integration of sine, we know, is negative cosine of u from 0 to pi. I'm going to plug in my cosine of pi minus the negative cosine of 0. Cosine of pi, that's negative 1, isn't it? Then minus cosine of 0, that's going to be a 1 as well. So we have negative of negative 1 minus a negative 1. So I get 1 plus 1, or 2. And then I really wanted to spend a little bit of time on even-odd functions. I don't necessarily get too hung up on even and odd functions. However, you should recall from your pre-calculus days that if a function is even, then f of negative x equals f of x. And remember, again, that is symmetric with the y-axis. So our friend here, f of x equals x squared, is definitely an even function. So what that means is that if I have a value here at x, and come up, it's going to equal the same value at negative x. If I drew these correctly, what would you notice about the two areas that are created here? I'll let you think about that for a second here. All right, and then for an odd function, recall our friend the cube, x cubed, f of x equals x cubed. Again, if we have an x, then if we look at negative x, it's going to give us the negative y value. And again, I'm going to ask you to think to yourself, well, what do you know about these two areas? And when we talk about integration. So up here with an even function, what did we notice? Yeah, they're the same, aren't they? So if I know the integration from 0 to x, I can also come up with from negative x to x, because 0 to x is going to be half of everything. Or if I multiply this area by 2, I get the total. Whereas an odd function, they're going to negate each other. We have the same amount below the x-axis as we have above the x-axis. Remember, we integrate from negative x to 0 here below the x-axis, it gives a negative value. And when we integrate above the x-axis, we get a positive. So two things that we can see. If we have an even function, and we go from negative a to a of f of x dx, it's equal to 2 from 0 to a of f of x. And an odd function from negative a to a is going to be 0. So let's look at the sign of x from negative pi over 2 to pi over 2. Well, the first thing we have to do is figure out, well, what does the sign of x look like from negative pi over 2 to pi over 2? So it goes back to our algebra 2 days here of graphing the sign of x. And if you don't remember the graph of the sign of x, well, that's going to be a little bit of an issue. But if we look at the unit circle again, and we look at that value here, we have 1, 0. Maybe I don't know my unit circle. So we have 1, 0 here. The sign of 0 is going to be 0, isn't it? So that gives you that reference point, and then hopefully you can go ahead and draw in the rest of your sign function. So if we look from negative pi over 2, and that goes back into our arcs, doesn't it? Arc signs for the domain. So if I look at this, I should see that we have the same area below and the same area above. So I know this is an odd function, so it's going to be 0. Now, we could also go ahead and test for that symmetry. We could definitely think about the sign of negative x, and what does that equal? Well, if you recall the sign of negative x, what happens with that value? All right, that value is going to end up being the negative of the sign of x. All right, so that tells you, again, that's kind of the proof that we have an odd function. So that's going to end up giving us 0. Here's really the way they like to kind of test this. It didn't really come out very clear, I don't see on my computer here. But they like to test it in this form. If we know the integration from 0 to 3 of f of x dx is some value, and they tell us that it's an odd function, well, in my mind, what I'm going to do is I'm going to kind of draw a figure, and it doesn't matter what that figure is. It can look something like that. And if I go from 0 to 3 here, then if it's an odd function, I know it's going to come out like this, because we're going to rotate around that origin. So what do I know? Well, from negative 3 to 3 of that, I have this here area, and this area here is going to negate that, so I'm going to end up with 0. If I go from 0 to 3 of the negative f of x, so if I take this area, but I take the negative of it, I'm going to end up with a negative 20 1/4. And here I'm going to go from negative 3 to 0. Well, if I know from 0 to 3 is 20 1/4, then from negative 3 to 0, that's going to be below the x-axis. That's going to be a negative 20 1/4. So that kind of gives you an idea of how they would necessarily test this. So you can use it definitely to make your life a lot easier thinking about a function. If we go back to this, actually, we have a little bit of time. Do we necessarily have to put this in and know that it's an odd function? Of course not. We know the integration of sine. The integration of sine is negative cosine of x, isn't it? From negative pi over 2 to pi over 2. Well, if I plug in my pi over 2, I get the negative cosine of pi over 2 minus a negative cosine of negative pi over 2. And again, we can think about the cosine of pi over 2. Cosine of pi over 2 is 0. And then minus cosine of negative pi over 2. Cosine of negative pi over 2 is 0 as well. So we have the minus a negative 0. 0 plus 0 gives us 0, doesn't it? So we don't necessarily have to remember that we have a function that's even or odd. However, it makes your life a little easier because you don't have to go through all of this work. So that gives you kind of an idea of where we see our even and odd functions, as well as that definite integration, changing those x values to u's. If you have questions, let me know. Good luck, enjoy. Happy integrating.